In this video, we're going to introduce inverses of functions. So there's lots of instances in everyday life where you talk about doing something and then undoing that thing. As a simplistic example, you certainly put on your shoes and socks before you go outside, or at least I presume you would, before you go outside before you leave the house. When you come back in, you're going to take your shoes back off and then your socks. So there's lots of things that you would need to do and undo, and that's the idea of an inverse of a function. It's going to undo whatever the original function does. So we can do this in terms of relations. Remember that a relation is a set of ordered pairs. So if we want to do the inverse of any relation, we can just simply reverse the ordered pair. If we think of x being input, y being output, the inverse is going to reverse that role, so the y would be the new input, the x would be the new output. So for anything, any ordered pair in the relation, the inverse relation is made up of the ordered pairs that simply flip-flop the x's and the y's. So as a specific example here, let's say we have the relation that contains the ordered pairs 1, 4, 1, 7, 2, -3, 3, 5, and 5, 2. Then the inverse relation is simply, again, just taking those ordered pairs and reversing the x and the y coordinates. So for the inverse relation in this case, we get 4, 1, 7, 1, -3, 2, 5, 3, and 2, 5. If we had something where we have a function or a relation, an equation that gives us a relation, so if maybe in this case the relation is the actual function here, y equals x squared, then if we want the inverse relation, again, we're going to reverse the roles of x and y. Rather than reversing them here in the ordered pairs, I can just reverse what x and y are in the equation. So rather than having y equals x squared, we'll have x equals y squared, which exactly reverses the roles of what's going on with the x and y. In the first relation, the x is what's being squared. In the second relation, it's the y that's being squared. So if we looked at a specific graph here, the red graph is the graph of the original relation, or in this case, like I said, the original function, y equals x squared. Then the graph of the inverse relation, where we flipped the roles of x and y, we get a sideways parabola, x equals y squared. So just again, with the way that the inverse relation is defined, here is a point x comma y on the relation. The point y comma x is on the inverse relation, and what we notice is that the graph of the inverse relation is a reflection of the original one about the line y equals x. And again, the reason for that is because we're reversing the roles of x and y. So a reflection about the line y equals x does that graphically. So this is what I just mentioned. The graph of the inverse relation is the original graph reflected about the line y equals x. So one thing that we notice when we do this reflection is that if we reflect a vertical line around that line, it becomes around the line y equals x, it becomes a horizontal line, and vice versa. Let me go back up to that graph. If I imagine a vertical line going this way, if I reflect about the line y equals x, it becomes a horizontal line going this way. Because if you think about reflection, if it's coming in this way, this would be a 45-degree angle. It's going to go over a 45-degree angle again. And then vice versa. If I take a horizontal line, it's going to reflect to a vertical line. So, in that previous example, we noticed that the inverse relation was no longer a function. Y equals x squared is a function. X equals y squared is not a function, at least not a function of x. So, and again, the reason for that is because that original function did not pass the horizontal line test, which means its inverse relation isn't going to pass the vertical line test. Because if we think about a horizontal line going across, make scroll back again, think of a horizontal line going across here, it intersects 2 points. In the inverse relation, it's also a vertical line is going to intersect in 2 points. So that's exactly what we call the horizontal line test. I know I just mentioned those words a second ago. But the horizontal line test is a way to tell whether or not a function has an inverse that is also a function. In this case, that is no, right? The inverse relation here is no longer a function because it doesn't pass the horizontal line test. The original function does not pass the, the inverse function does not pass the vertical line test, and the original function does not pass the horizontal line test. So let's see if we can state that a little bit better here with another example. Here's a function. Notice it, if I take a horizontal line in some places, it intersects several times. Any horizontal line going this way would intersect 4 times. Ones up here intersect twice. That function does not pass the horizontal line test. If we look at the graph of its inverse relation, notice here's the inverse relation, again flip-flopping across the line y equals x. It does not pass the vertical line test. So in this case, this function has an inverse that is not a function. Versus, here is a function, this first one, that passes the horizontal line test. Any horizontal line intersects at most once. When you do the reflection around the line y equals x, you get something that passes the vertical line test, and we really do get a function. So the inverse of this function is itself also a function. All right, so let's look at a definition here. We say a function is one-to-one if whenever the outputs are the same, the inputs are the same. So if you plug in 2 numbers into the function and get the same output, if it's one-to-one, it means you plug the same number in twice. So if we reverse the way that's said, distinct inputs for one-to-one functions result in distinct outputs. So what the horizontal line test is really telling us is whether or not a function is one-to-one. Because if I scroll back, here is something that doesn't pass the horizontal line test. Now here, let's just look at the x-axis. Notice at -2 and at 0 and at 2, we've got 3 separate inputs that give us the same output, not one-to-one. Okay. Scroll back over here. So the horizontal line test again tells us if a function is one-to-one. So we can say that a function has an inverse function if and only if the function itself is one-to-one. All right, so let's do an example now of actually finding an inverse function. So let's say we have the function f of x equals 3x minus 2 over x plus 1. Here's the process for going through this. So the first thing I want to do is just call f of x y, just for simplicity's sake. So we always identify the output of a function with the y coordinate anyway, so I might as well just call it y equals 3x minus 2 over x plus 1. Now remember, inverses reverse the roles of x and y. Doing that in here, I'll just interchange wherever I see a y, I'm going to put an x. Wherever I see an x, I'm going to put a y. So we get x equals 3y minus 2 over y plus 1. And now we want to solve for y. So this whole stack over here is what we get when we solve for y. We multiply both sides by y plus 1. So we get x times y plus 1 equals 3y minus 2. Again, we're trying to solve for y, so we're going to gather the y's. In order to gather the y's, we're going to need to distribute on the left-hand side first and get xy plus x equals 3y minus 2. Gather all the y's to one side, so we'll subtract 3y over to the left-hand side and subtract x over to the right-hand side, so we'll get xy minus 3y equals negative x minus 2. The reason why we gather all of our y's to one side is that it allows us to factor out a y, so we get y times the quantity x minus 3 equals negative x minus 2. And then finally, to solve for y, we just need to divide both sides by x minus 3. To get us y equals the negative of x plus 2 over x minus 3. And this negative out in front is just coming from factoring a negative sign out of the negative x minus 2 that we saw in the previous step. And then finally, to denote that we really have found the inverse function, we're going to replace y with a notation, what looks like it says f to the negative 1 of x. Don't be confused by this notation. This is notation for the inverse. If you're familiar with negative exponents, does not mean take the reciprocal. Okay? I know it's confusing notation, but that negative 1 that looks like it means a negative 1 exponent is not what it means in the language of inverse functions. It means take the inverse of it. So this is the inverse of f inverse of x is the negative of x plus 2 over x minus 3. All right, so let's see if we can find the inverse of this f of x equals x plus 1 to the fourth minus 3, and we're going to restrict the domain as necessary. So let's talk about what we mean by that. All right, if we look at the original function, here's the function f of x plus 1 to the fourth minus 3. Notice this is the function x to the fourth, our basic function x to the fourth. We've shifted it left 1 unit and down 3 units. So that's why the graph looks like this. This function does not pass the horizontal line test, which means if we look at the inverse, it's not going to be a function unless we restrict. So how do we decide how to restrict? Well, we usually restrict by looking at two things. One, we want to make sure that the function is still 1-to-1 when we restrict. So I wouldn't want to restrict, say, here, because that piece wouldn't be 1-to-1. We want to restrict so that it's 1-to-1, and we also want to take up the full complement of range values. So I wouldn't want to just say this piece, because I got a whole part of the range that's missing. So when we do the restriction, we're going to want a full complement of range values. So over here I've shown one such restriction, starting off here at the bottom and going up and to the right forever. So restricting from -1 to positive infinity for the x's, restricting the domain. I could have also used the left-hand side and gone from -1 to negative infinity up to -1. So we had two kind of possible restrictions using the idea that we want to make sure our restriction, the function on the restriction is 1-to-1, and make sure that we take up a full complement of range values. All right. So like I mentioned here, the original function, not 1-to-1. So the inverse will not be a function unless we restrict. So we're going to restrict to where they're 1-to-1 and take up the entire range. So we've identified already that we want to use -1 to infinity for our restriction. Okay, so let's do the inverse based on this restriction. So we're going to do the exact same thing we did in the previous example. We're going to change f of x to y. We're going to exchange x and y. And we're going to start solving for y. So the first thing we'll do is add 3. We'll do the fourth root of both sides to get y plus 1 equals the positive fourth root of x plus 3. The reason why we use the positive root here is because we restricted on the right-hand side of that graph. Remember, fourth roots, you can get plus or minus, just like you can do for square roots. If you do a fourth root of both sides, you're going to get plus or minus. We have to make a choice, and we chose to use the positive fourth root by our restriction. Then subtract 1 from both sides to get y equals -1 plus the fourth root of x plus 3. And that's exactly now what our inverse function will be. All right, so when we talked about at the beginning, we said that functions undo, or inverse functions undo whatever the original function does. So notice that in this previous example here, the function takes an input, adds 1, does the fourth power, and then subtracts 3. If we look at what the inverse does, here's an input. What was the last thing we did here? We subtracted 3. The inverse, that's the first thing it undoes. It adds the 3 back. Original function, what was the next to last thing we did? We did a fourth power. What's the inverse function do at this point? Take a fourth root. What was the first thing we did here? Added 1. What's the last thing we do here? We subtracted 1. So we're going to undo each of the operations that we did in the original function. We're going to just undo them in the reverse order. It's not unlike the taking your shoes and socks off. In the morning, you put your socks on, and then you put your shoes on. When you come home at night, you got to take those shoes off first before you take off your socks. Otherwise, you're going to put a giant hole in your socks. All right, so this all leads us to an important statement about functions and inverses. So for a function f and its inverse f inverse, we have, if I compose f with f inverse of x, I have to get back where I started from. So if I take the inverse function and then apply the original function, I get back to where I started. That has to be true for all x in the range of f, which is the same as the domain of f inverse. Remember that inverses reverse the roles of x and y. Range would be the set of all y's for the function. So the range of the original is the domain of the inverse. And we need to make sure that we have this statement because we need to be able to plug it into the inverse function to start with. Also, if we reverse the order, if we do the inverse composed with the function, we get back to where we started. And this is true for all x in the domain of f because we got to be able to plug it into the inside function here first. But the domain of f is the same as the range of the inverse function. So let's look at a specific example of this property. It says verify that we really do have inverses here if we have the function f of x equals 2 over x plus 1 and the inverse function is 2 minus x over x. So again, to verify that we really do have inverses, we compose the two functions together and see that we get x. So if I do f of f inverse of x, that's f of 2 minus x over x. So in the function f, we're going to replace the x with 2 minus x over x. Get a common denominator in the denominator. So we've got 2 over 2 minus x over x plus x over x. Adding those two things in the denominator gives us 2 over x. When we divide by a fraction, we multiply by the reciprocal, so we get 2 times x over 2, which gives us x. So we really did get back to where we started. Likewise, if we do the inverse composed with the original function, that gives us the inverse of 2 over x plus 1. So in the inverse function, we're going to replace x with 2 over x plus 1. That gives us 2 minus 2 over x plus 1 in the numerator, all over 2 over x plus 1 in the denominator. Get a common denominator in the numerator. So we'll multiply the 2 by x plus 1 over x plus 1. This is a typo. This should not just be over x. This should be over the 2x plus 1 from the previous step here. So this x is wrong. This should be 2 over x plus 1 here. Should be the same thing here, if you're taking notes along with this. All right, when we simplify the top, if we distribute the 2 through, we get 2x plus 2, and then we'll get a minus 2. So on top, we get the fraction 2x over x plus 1. And on bottom, like I mentioned, we'll have the 2 over x plus 1. Dividing by a fraction is the same as multiplying by the reciprocal, so we have 2x over x plus 1 times x plus 1 over 2, and that simplifies to x.